All right, the main reason for this video is to do a test of hypothesis for a population proportion. But before I do that, I want to touch base with one of the topics I was talking about recently, and that was p-values. And so in this slide, I want to compare p-values and rejection regions. There are two different techniques for making conclusions in a test of hypothesis. And I want to show you on one page both of them so you can kind of compare them and see what's going on. So to do this, what I want to do is have a specific example. So you can see here in the upper right, I have a greater than test. We want to test mu is equal to 50 versus the alternative greater than 50. And I want to work with a sample size of 100. Sample size is an interesting topic in this particular video because I am going to be working with proportions in a bit. And 30 or more is not related to proportions at all. However, when you're doing a test for a population mean, 30 or more is considered a large sample. The reason I'm doing this is because what I want to do is work with the z-distribution. In fact, I want to work with the upper tail of the z-distribution. So I really want to zoom in. So I'm going to draw a giant z-distribution. And so what you're looking at here is the upper tail of a z-distribution. Okay? So think about this just monster z-distribution taking over the world as we speak. I'm looking at the upper tail, and typically what we do, I'm going to start with a rejection region. Typically what we do is we take a look at the tail, and because it's a greater than, I'm going to go to the upper tail of the z-distribution, and I'm going to put alpha in that upper tail. Remember, we take our alpha and we look at the alternative, and based on the alternative, we put the alpha in that particular location, whether it's a greater than like I have here. A less than, would flip this thing around. If it was a two-tailed, I would split alpha and put in both sides. And I guess I should mention here that the ideas I'm going to talk about on this slide are true regardless of which direction you're looking at. Obviously, I'm looking at a greater than example, but the same concepts and principles would hold true for the less than and also a not equal to test. It works for large and small samples. It works for means and proportions. These are just some general ideas about p-values and rejection regions that always apply. Okay. So I'm going to put alpha there. I'm going to find a critical value. We call it something like z if it's a large sample like this case, or t alpha. And we compare our test statistic to it. So here's what I want to do. Let's suppose that I have a value of a test statistic that falls out here. Okay, so maybe this is, we'll just say test statistic. I'll put TS for test statistic. The rejection regions compare the test statistic to z alpha, and so our rejection region would say something like at alpha equal 0.05, we're going to reject if our test statistic is bigger than the z alpha, and in this case it is, of course. And so in this case, where I've drawn the test statistic, this would be a rejectable test statistic. We'll reject H naught at this level of alpha. Now, if the test statistic were further out here, maybe like over here, I'm still going to reject, right? But what if the test statistic were, I don't know, maybe something like right here, and I'm trying to draw it real close and I didn't get super close. We're still rejecting, but just barely. Now what I'm going to do is hopefully I can do this. Yeah, look at that. Let's go back to the original. So here's what I'm going to write. I'm going to say if the test statistic is out here, this is where we reject the null hypothesis. And I'll just write it this way. Put a big arrow out there. If the test statistic is on this side, what do we say on this side? Well, if the test statistic showed up over here, this would be a fail to reject the null hypothesis, okay? So you can see why we call the z alpha thing a critical value. Depending on which side of that rejection region, that critical value, the test statistic falls, that dictates what we're going to do for our conclusion. And that's the rejection region picture, and that's the method that we use to make conclusions. Haven't brought in the p-values at all. So, all right, let me see if I can do this now. Let's get rid of this guy. Is it going to make me do them one at a time? It sure is. Look at that. All right, so when I want to bring the p-values into play, the p-values that we talked about, we draw the distribution, which I've got this giant curve. We draw in the value of the test statistic, which I'm just emphasizing it right here. And then we shade appropriately. So I'm going to shade in a different direction with a different color pen right now. And I'm going to shade to the greater than side. And this red shaded region would be considered our p-value. Okay, we take the test statistic and we shade, in this case, we're going to shade the greater than side to the right. And so that would be my p-value. And we should know, you should know that the p-values compare p-values to alpha. When p is low, when the p-value shaded region, the red shaded region in this case, is smaller than the alpha, the black shaded, and you'll notice there's less area in the red than there is in the black. P is low. That's a reject H0. All right, now I'm going to ask you a trick question now. I'm going to change colors of ink here. I'm going to go to blue. If my test statistic were out here instead, okay, this is a trick question. I think it's okay to ask trick questions when you start by saying it's a trick question. What happens to alpha? When my test statistic moves down here, what happens to alpha? Now I'm hoping you got it right. What happens to alpha? Nothing. Alpha is not related to the test statistic at all. What changes when the test statistic moves out here? Well, the shaded region beyond it, the new p-value, gets smaller. As the test statistic heads further out in the tail, the p-value is going to get smaller. So if the original p-value that I talked about, this red value here, was less than alpha, this is lesser than alpha. It looks smaller by comparison. So that's still a reject. So it's not real interesting to what happens with the test statistic as it moves further out. What is interesting, however, what happens when the test statistic goes here? Which is bigger, alpha or the new p-value? How about here? And again, I'll try to live life really on the edge here. What happens if the test statistic, whoops, falls right there? Well, now the p-value comes all the way over to that mark, but it's still smaller than alpha. The point I'm trying to make is when the test statistic jumps over this critical value, when the test statistic comes here, that's exactly the same time the relationship between alpha and the p-value changes. At precisely the moment the relationship between the test statistic and z-alpha, at precisely the moment you're going to change your conclusion here, that's the same moment that the relationship between alpha and the p-value changes as well. One of the things I hope you get out of this, one of the items, one of the pieces of information I hope you get out from this picture, is that it doesn't matter which technique you use, p-values or rejection regions, you're going to make the same decision regardless. Both are fine. Now, what I'm going to do next, the other piece that I want you to get, is I want you to see that these two things are a team. When you give me the test statistics, I'll switch to still another color. When I go with the green, when you give me the test statistic, well, there's a shaded region beyond that. The test statistic and the p-value match up. Typically, we calculate test statistics and then we go find them in tables. Or, this is the stuff that we get on the computer printout. Right? Most computers give us the test statistic and the p-value. And we've talked about before how sometimes the p-value isn't exactly the one we want, but we can find it. It's usually pretty easy to get the p-value from that printout. Sometimes we just take the number right off it. Sometimes we have to divide it in half or multiply by 2. Likewise, these two things are a team as well. Typically, I say, give me, let's test it alpha equal 0.05. You go find the critical value. In this case, it'd be 1.645. If I say alpha is 0.01, in this case, it'd be 2.576. And we've gotten pretty good. Hopefully, you've gotten really good at working with the tables. But these two things are a team as well. The challenge here is the z-alpha, that's you. You have to find the z-alpha from the table. Or maybe it's a small sample and it's a t. But that's work to do. So when it comes to making conclusions, here are your two choices. If you decide to use the rejection region approach, I say, hey, we're going to test it at alpha equal 0.05. The test statistic, you're going to get that number off the printout. Now you have to take your alpha of 0.05. You got to go to the z table. You got to convert it to a z value. Again, not real difficult, but there's a little bit of work there. And if I say, oh, did I say alpha equal 0.05? I really meant alpha equal 0.03. 0.03? No, I meant 0.02. Every time I tell you alpha, you're heading back to that table over and over and over and over again. Again, the tables aren't overly difficult, but it's work. It's work you're going to do. If you decide, however, to use the p-value method, take the p-value from the printout, and again, you may have to manipulate it a little bit. You may have to halve it or double it, depending on what the printout looks like, and compare it to alpha. If I say we want to switch alpha, just compare it to the p-value. And a lot of times, and I've said this before, students think, hey, I like the p-value method. There's no tables involved. Not true. The table's involved in the calculation of the p-value that the computer will do for you. That's why I'm such a big fan of the p-value method. Let's let the computer do as much of the work for us as we can. Both will work. I'm going to ask you to work with both. So you need to know how to work with rejection regions and p-values. But if you're given a choice, the p-value method is the way to go. Sometimes you'll be given a choice, sometimes you won't. I'll make you work with at least one rejection region on your final exam. All right, so that's my conversation regarding p-values and rejection regions. Usually it takes about 10 minutes. I think I'm right on that time frame. So let's talk about tests of hypothesis for a population proportion. We have a test that involves a null and an alternative. Now, the hypothesized value is going to be not mu naught, it's going to be p naught. A proportion, we're working with qualitative data now. A proportion is equal to some hypothesized value. Maybe we're saying p is equal to 40%. Maybe someone's saying p is not equal to 40%. What are your three choices here, do you think? Hopefully you're playing along now. You know you're going to have to choose the less than, the greater than, or the not equal to. You have three choices for the alternative. We always use the equal sign in the null. The test statistic is the sample stuff. A lot of copy and pasting going on in your notes right now. Straight from your large and small sample test for mean, the thing that changes, the symbols of the formula change. Again, you're not going to do this math. We're going to let the computer do the math for us. In another video, I'll show you how to do test hypothesis for a population proportion. One of the pieces you'll see on the printout is the test statistic. Another piece is the p-value. So the test statistic is still the same, and now you have to evaluate it. Oh, I should mention here, now's a good time to mention it. You see a z here? We're going to assume that we have a large sample, or better yet, let's say we need a large sample. What's a large sample? N times p has to be greater than 15, or at least 15. Let's make that greater than or equal to. N times q also. What's q? Q is the opposite of p. So if p is 0.4, q is 0.6. Now, in the math, we got a couple different values. When we were working with confidence intervals, we took sample proportions. So it was actually n times p hat and n times q hat. But in a test to hypothesis, we believe the null is true. And so in the formulas here, we're going to take n times p naught and n times q naught. So a similar sample size determination to what we saw when we were working with confidence intervals. It's messy, it's ugly. It's not nearly as easy as 30 or more, but it's the one I want you to use. So we need n times p and n times q to be greater than or equal to 15. When it comes time for small samples, if you follow along, you'd probably say, well, rather than a z, what do you think we'd use? We'd want to use a t, right? It would have n minus 1 degrees of freedom. We've heard that before. What assumption we need? Well, for the t-distribution to work, we always need the population of x's to be approximately normal. Except now I'm not working with numbers. I'm working with categories. I'm asking you, do you have this characteristic or not? Yes or no? When you have yeses and nos, you're never going to get a normal population. That normal assumption that's needed for the t-distribution never works with proportions. And so we can talk about what we could use with a small sample, but it'll never work. And so for proportions, you need large samples. You need n times p naught and n times q naught to be at least 15. If you don't have that, you can't do this. So you got to make sure you're working with large samples with proportions. All right, once we know large sample, we can evaluate the test statistic. There's rejection regions, there's p-values. And when we work with p-values now, because I'm talking about a large sample, maybe I'll ask you to find a p-value for a proportion problem. You should be able to go to the table and find the p-value in the table. I'll take a look at that with the example I do. I'll show you how we do that again. I'll give you another example of that. And then we make our conclusion. We either compare the test statistic to the rejection region or we compare alpha to the p-value. It's the same thing. It's just another example of a test to hypothesis. So it'll look like this. At alpha equal 0.05, if we reject, they're sufficient. If we fail to reject, I'll do double lines here, there'd be insufficient evidence to indicate that the alternative is true. It's just another test to hypothesis. So what I want to do is go through an example with you. And in the example, I'll do both the rejection region and the p-value approach, and we'll go from there. So the example deals with streaming of television programs. Old data, 2013 study claimed that 1/3 of all Americans qualify as subscription streamers. Netflix, Hulu, Amazon Prime, there's plenty of others out there. A recent study of 2,242 elderly adults. You guys would probably put me in that group. I don't like to think I am, but maybe my age and above. Are they streaming too? We tend to be less technology oriented. So in the study of elderly adults, 785 of the 2,242 were considered subscription streamers. I am. On the basis of this sample, can we conclude that the true fraction of elderly adult subscription streamers, tough for me to say apparently, differs from 1/3? We're going to test using alpha equal 0.10. I want you to be able to go through the 4 steps. I want you to be able to find the test, specify the null and the alternative, get the test statistic, evaluate it, make a conclusion. So how do we see if a proportion, I said fraction here, proportion, percentage, rate, all different words that mean the same thing, differs from 1/3? How's that look? P is not equal to 1/3. We put an equal sign. We drop an equal sign. The equal sign always shows up in the null. That's what we're testing. I need to go and get a test statistic. Well, where's that come from? It comes from the formula. I don't want to do the math, neither do you. We're going to go to the computer and we're going to get a printout that looks something like this. This is the software that we're using. Here's the test statistic right here. You'll notice right next to it there's a p-value. We'll come to that in a bit. There's the test statistic right there. They want us to do this test at alpha equal 0.10. Now here's my point. If you're a p-value person, you got to decide, is that the p-value that you want to use? We'll talk about it in a minute. But it's right there. It's really easy. The first technique I'm going to use is the rejection region approach. Okay, the rejection region approach says, well, first, is this a large sample problem? We got to take a look at n times p naught, which is 2242. Remember the days when we could use 30 or more? Yeah, they're gone. Times p naught. Well, p naught is 1/3, and I'll just write it this way. This number is 747.3. That's bigger than 15. That's at least 15. N times Q naught. 2242. What's Q naught? Well, Q naught is the opposite of P naught. So if P is 1/3, Q is 2/3. This is an even bigger number, 1494.7. That's a 0.7, 1494.7. Again, drawing with a mouse. Both these things are greater than or equal to 15. N is large. 30 or more is so much easier to work with. It also doesn't work with proportions. You got to remember that. If it was means, if I ask these elderly adults, how many hours do you spend on your subscription streaming per week? And I wanted to estimate the average of that time. This is a large sample because n is greater than or equal to 30. But because this problem deals with proportions, I got to go through this n times p naught, n times q naught. It is not nearly as easy. It is a pain in the neck. It is the same as when we did confidence intervals. When we compare two proportions in the next chapter, it's going to be the same there too. So they're just different sample size criteria you're going to work with. All of that to say, hey, guess what, guys? We can work with a z-distribution. We have a large sample problem. And so in this z-distribution, we're going to go and put alpha of 0.10. Where's it go in a not equal to test? Well, it goes in both places. But I can't put 0.0 or 0.10 in both sides. What do I have to put? 0.05. Put 0.05 here. And now I have to go and find these critical values. My hope is that you've looked at a lot of these problems and you know what these numbers are. If you don't, fortunately for you, whoops, I thought I had a z-table. Apparently I don't. The z-table or the t-table, depending which table you're going to look at, if you're looking up a z-table, you're going to use this inside probability of 0.4500, and you're going to find that that value happens between 1.64 and 1.65. If you're working with a t-table, you go to the 0.05 column all the way down the bottom, and you're going to find this 1.645 number. It's two sides. So we're going to reject if our test statistic falls below 1.645, negative 1.645, or above a positive 1.645. What's our test statistic? 1.69. We can reject. There's sufficient evidence to indicate that the alternative is true. P is not equal to 1/3. The true fraction of all elderly adult subscription streamers differs from 1/3. Test statistic, rejection region, conclusion. The only thing we need here is a random sample. That's the only assumption that's necessary. How about the p-value? Well, the p-value, to find the p-value, it's going to be right there on the printout, but here's the picture that generated it. Now, before I draw the picture and talk about that, we want to do a not equal to test. You can see on the printout that I have a not equal to test that's specified here. I'm just underlining that's not an equal sign. This p-value is the correct p-value for the not equal to test. Where it came from is the computer did this. It said, hey, you know what? Let's put the test statistic out here at 1.69, and then the p-value looks at what test statistics are further out there in the tail. Well, further out in the tail when you're doing a not equal to test include all these guys and all of these guys out here. These two shaded regions together, if you go to the Z table, are 0.0909. When you have a printout, you don't have to find them in the table. And sometimes when you go to the table, you're going to be off a little bit because the test statistic isn't really 1.69. It might be 1.684173332. So it might be off just a smidge. In fact, when I went to the Z table, I found a 0.4545 in here. No, I'm sorry, 0.0455. I got that wrong. 0.0455. That's not right. Say that again. I'm getting trouble. I'm having trouble with numbers. 0.4545. 0.4545. Let's try that again. There we go. That's the inside probability. So the outside probability is 0.455. You can see why all these numbers are looking the same. So the shaded region over here is 0.0455. And the shaded region over here is the exact same. So when I did my math, when I did it by hand, I actually got the p-value of 0.0910. And you can see it's a little off, but it's off because this test statistic's been rounded to 2 decimal places. Not a big deal. Point is, if you have the p-value on the printout, use it. If you have to find it in a table, be prepared for that. But now, make your conclusion. Is p low? Is p lower than that alpha? Yeah, it is. 0.09 is just barely, but it's lower, so we can reject. There is sufficient evidence to indicate that the true fraction, true proportion, true percentage of all adults subscription streamers differ from 1/3. Rejection regions and p-values will always give you the same conclusion. You got to be prepared to do both. All right, that's where I'm going to stop testing for a single proportion. We've looked at mean large samples. We've looked at mean small samples. We've looked at proportions, only large samples for proportions. We turn our attention next to comparing two means and proportions, but I'll do that in another video. Do some homework problems, get your questions asked. Good luck.